3.1.2 Extended Euclidean Algorithm. Using the Euclidean algorithm, we can determine when A has an inverse modulo M by testing whether the greatest common divisor of A and M equals to 1. GCD of comma A comma M, parentheses, A comma M, close parentheses, equals 1. So let's see, that just says it has an inverse if they're relatively prime. But we still do not know how to determine the inverse when it exists. To do this, we use a variant of Euclid's GCD algorithm, greatest common divisor algorithm, called the extended Euclidean algorithm. Recall, we had r sub I minus 2 equals q sub I minus 1 times r sub I minus 1 plus r sub I, with r sub m equal to the GCD of r sub 0 and r sub 1. So r sub m is the greatest common divisor of r sub 0 and r sub 1. Now we unwind the above and write each r sub I for I greater than or equal to 2 in terms of a and b. For example, r sub 2 equals r sub 0 minus q sub 1 r sub 1 equals a minus q sub 1 b. R sub 3 equals r sub 1 minus q2 r2, which is equal to b minus q2 parentheses a minus q1 b1 equals negative q2a plus parentheses 1 plus q1 q2b. This is the extended Euclidean algorithm. Dot, dot, dot. R sub I minus 2 equals S sub I minus 2a plus T sub I minus 2b. R sub I minus 1 equals S sub I minus 1 times a plus T sub I minus 1 times b. R sub I equals R sub I minus 2 minus Q sub I minus 1 times R sub I minus 1, which is equal to a parentheses S sub I minus 2 minus Q sub I minus 1 S sub I minus 1 close parentheses plus b parentheses T sub I minus 2 minus Q sub I minus 1 T sub I minus 1 close parentheses dot 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 R sub m plus S sub m a plus T sub m b. The extended Euclidean algorithm takes an input a and b and outputs r sub m, s sub m, and t sub m such that the r sub m is the greatest common divisor of a and b, which is the s sub m times a plus t sub m times b. Hence, we can now solve our original problem of determining the inverse of a modulo n when such an inverse exists. We first apply the extended Euclidean algorithm to a and n so as to compute dxy such that d is the greatest common divisor of a and n, which is x times a plus y times n. So the d, the divisor, is xa plus yn. We can solve the equation ax equals 1 mod n, since we have d equals xa plus yn equals xa parentheses mod n. Hence, we have a solution x equal a to the minus 1 precisely when d equals 1. As an example, suppose we wish to compute the inverse of 7 modulo 19. We first set r sub 0 equal to 7 and r sub 1 equal to 19. And then we compute r sub 2 equals 5 equals 19 minus 2 times 7. r sub 3 equals 2 equals 7 minus 5 equals 7 minus parentheses 19 minus 2 times 7, close parentheses, equals negative 19 plus 3 times 7. r sub 4 equals 1 equals 5 minus 2 times 2 equals parentheses 19 minus 2 times 7, close parentheses, minus 2 times, open parentheses, negative 19 plus 3 times 7, close parentheses, which equals 3 times 19 minus 8 times 7. Hence, 1 equals negative 8 times 7 mod 19. And so 7 to the negative 1 is negative 8 is 11 mod 19. (3.2) The Chinese remainder theorem, CRT. The Chinese remainder theorem, or CRT, is also a very old piece of mathematics, which dates back to at least 2,000 years. We shall use the CRT in a few places. For example, to improve the performance of the decryption operation of RSA, and in a number of other protocols. In a nutshell, the CRT states that if we have the two equations, x equals a mod n and x equals b mod m, there is unique solution m times n if and only if the greatest common divisor of n and m is 1. In addition, it gives a method to easily find the solution. For example, if the two equations are given by x equals 4 mod 7 and x equals 3 mod 5, then we have x equals 18 mod 35. It is easy to check that this is a solution, since 18 mod 7 equals 4, and 18 mod 5 equals 3. But how do we produce this solution? We shall first show how this can be done naively, from first principles, and then we shall give the general method. We have the equations x equals 3 mod 7 and x equals 3 mod 5. Hence, for some u, we have x equals 4 plus 7u and x equals 3 mod 5. Putting these latter two equations into one gives 4 plus 7u equals 3 mod 5. That's because x is equal to 3 and he substituted 3 in for x. So x equals 4 plus 7u, x equals 3 gives 3 equals 4 plus 7u. All right, in mod 5. We then rearrange the equation to find 2u equals 7u. That's mod 5, right? So 2u equals 7u equals 3 minus 4, which equals 4, mod 5, right? 3 minus 4 is negative 1. Add 5 to it, you'll get to 4. All right, so 2u equals 7u equals 3 minus 4 equals 4. So 2u is 4 and 7u is 4. Now, since the greatest common divisor of 2 and 5 is the greatest common divisor of 7 and 5 equals 1, we can solve the above equation for u. First, we compute 2 to the negative 1 mod 5. That's 3. Since 2 times 3 equals 6 equals 1 mod 5, so he's multiplying 2u by 3, its inverse. So 2 times 3 is 6, which is 1 mod 5, so the other inverses. Then we compute the value of u equals 3 times 4 mod 5. 2. Then substituting this value of u back into our equation for x gives the solution x equals 4 plus 7u equals 4 plus 7 times 2 equals 18. The case of two equations is so important, we now give a general formula. We assume that the greatest common divisor of n and m equals 1, and that we are given the equations x equals a mod m and x equals b mod n. We first compute t equals m to the negative 1 mod n, which is possible since we have assumed the greatest common divisor of n and m equals 1. We then compute u equals parentheses b minus a close parentheses times t mod n. The solution modulo m times n is then given by x equals a plus um. To see this always works, we compute x mod m equals a plus mod m equals a. X mod n equals a plus mod n equals a plus parentheses b minus a close parentheses tm mod n equals a plus b minus a in parentheses times m minus to the minus 1 times m mod n. Equals a plus b minus a mod n equals b. I'm not sure what this t comes from. Oh, the t is m to the minus 1. Now we turn to the general case of the CRT, that's Chinese remainder theorem, where we consider more than two equations at once. Let m1 m sub r be pairwise relatively prime, and let a sub 1 a sub r be given. We want to find x modulo m equals m1 m2 m sub r such that x equals a sub I mod m sub I for all I. The Chinese remainder theorem guarantees a unique solution given by x equals the sum from I equals 1 to r of a sub I, capital M sub I, y sub I, mod m, where capital M sub I equals m divided by lowercase m sub I. Y sub I equals capital M sub I to the minus 1, mod m sub I. As an example, suppose we wish to find the unique x modulo m equals 1001 equals 7 times 11 times 13, such that x equals 5 mod 7, x equals 3 mod 11, x equals 10 mod 13. We compute m sub 1 equals 143, y sub 1 equals 5, m sub 2 equals 91, y sub 2 equals 4, m sub 3 equals 77, y sub 3 equals 12. Then the solution is given by x is the sum I equals 1 to r, a sub I capital M sub I, y sub I mod m, equals 715 times 5 plus 364 times 3 plus 924 times 10 mod 1001 equals 894. Legendre and Jacobi Symbols, Chapter 3, Section 3, or 3.3. Legendre and Jacobi Symbols. Let P denote a prime greater than 2. Consider the mapping f sub p to f sub p, where alpha goes to alpha squared. This mapping is exactly 2 to 1 on the non-zero elements of f sub p. Just think, I mean, if you had 1 and -1, 1 squared is 1 and -1 squared is 1. So that's two things going to the number 1. So if an element x in f sub p has a square root, then it has exactly 2 square roots, unless x equals 0. And exactly half of the elements of f sub p star are squares. The set of squares in f sub p star are called the quadratic residues, and they form a subgroup of order p minus 1 over 2 of the multiplicative group f sub p star. The elements of f sub p star which are not squares are called the quadratic non-residues. To make it easy to detect squares modulo p, we define the Legendre symbol, parentheses a over p, close parentheses. This is defined to be equal to 0 if p divides a. If it is equal to plus 1, it is equal to plus 1 if a is a quadratic residue, and it is equal to -1 if a is a quadratic non-residue. It is easy to compute the Legendre symbols. For example, via a over p equals a to the p minus 1 divided by 2, mod p. However, using the above formula turns out to be very inefficient. In practice, one uses the law of quadratic reciprocity. Q over p equals p over q times -1 to the p minus 1 times q minus 1 over 4 in the exponent. In other words, we have q over p would be negative p over q if p equals q equals 3 mod 4, and q over p would be p over q otherwise. Using this law with the following additional formulae gives rise to a recursive algorithm. So the Legendre symbol, q over p, equals q mod p divided by p. So q times r over p equals q over p times r over p. These are the parentheses around these, the Legendre symbol. And 2 over p in parentheses equals -1 to the p squared minus 1 divided by 8. Assuming we can factor, we can now compute the Legendre symbol. 15 over 17 is 3 over 17 times 5 over 17 by equation 3. Let's see, q times r over p is q over p times r over p. Yeah. Okay, so 15 over 17 is 3 over 17 times 5 over 17 by equation 3. And that's equals 17 over 3 times 17 over 5. So you can flip them upside down by equation 1. Oh yeah, q over p is p over q times -1 to this exponent. And 17 over 3 times 17 over 5 becomes 2 over 3 times 2 over 5 by equation 2. Equation 2 says q over p is q mod p over p. So 17 mod 3 over 3 and 17 mod 5 over 5. 17 mod 3. Yes, so that would be 2 over 3 times 2 over 5. All right, and by equation 4, 2 over 3 is -1. Right, 2 over p equals -1 to the p squared minus 1 over 8. And 2 over 5 is -1 to the third by equation 4, which equals 1. So I can expand a lot of the stuff in here with extra videos of my own. So maybe I'll work some of the stuff out in this book in separate videos. In a moment, we shall see a more efficient algorithm which does not require us to factor integers. Computing square roots of elements in f sub p star when the square root exists turns out to be an easy task. Algorithm 1.2 gives one method called Shanks Algorithm of computing the square root of a modulo p when such a square root exists. When p equals 3 mod 4, instead of the above algorithm, we can use the following formulae. X equals a to the p plus 1 over 4 mod p, which has the advantage of being deterministic and more efficient than the general method of Shanks. That this formula works is because x squared is a to the p plus 1 over 2, which is a to the p minus 1 over 2 times a, which is the Legendre symbol a over p times a, which equals a, where the last equality holds since we have assumed that a is a quadratic residue modulo p, and so it has Legendre's symbol equal to 1. The Legendre symbol above is only defined when its denominator is a prime, but there is a generalization to composite denominators called the Jacobi symbol. Suppose n is greater than or equal to 3. Suppose n greater than or equal to 3 is odd, and n equals p1 to the e1, p2 to the e2, ... p sub k to the e sub k. I guess that's a prime factorization, right? Then the Jacobi symbol a over n is defined in terms of the Legendre symbol by a over n equals a over p1 to the e1, a over p2 to the e2, ... a over p sub k to the e sub k. Those are kind of interesting connections, right? So algorithm 1.2, Shanks algorithm for square roots modulo p. Choose a random n until 1 is found such that n over p is 1. Let EQ be integers such that q is odd and p minus 1 equals 2 to the EQ. Y equals n to the q mod p, r equals e. X equals a to the q minus 1 over 2 mod p. B equals ax squared mod p. X equals ax mod p. So in that algorithm, while b is not equal to 1, mod p do. Okay, here we go. Find the smallest m such that b to the 2m equals 1 mod p. T equals y to the 2 to the r minus m minus 1 mod p. Y equals t squared mod p. R equals m. X equals xt mod p. B equals by mod p. Okay, and then end. So that stuff's in the middle of the while end. Then return x. The Jacobi symbol can be computed using a similar method to the Legendre symbol by making use of the identity derived from the law of quadratic reciprocity. A over n equals 2 over n to the e, parentheses n mod a sub 1 over a sub 1, and negative 1 to the a sub 1 minus 1, n minus 1 over 4, where a equals 2 to the e a sub 1, and a sub 1 is odd. We also require the identities for n odd. 1 over n is 1, 2 over n is negative 1 to the n squared minus 1 over 8, and negative 1 over n is negative 1 to the n minus 1 over 2. This now gives us a fast algorithm, which does not require factoring of integers to determine the Jacobi symbol, and so the Legendre symbol in the case where the denominator is prime. The only factoring required is that of extracting the even part of a number. 15 over 17 equals negative 1 to the 56, 17 over 15 equals 2 over 15 equals negative 1 to the 28 equals 1. Recall, the Legendre symbol, a over p, tells us whether a is a square modulo p for p a prime. Alas, the Jacobi symbol, a over n, does not tell us the whole story about whether a is a square modulo n. when n is a composite, if A is a square modulo n, then the Jacobi symbol will be equal to +1. However, if the Jacobi symbol is equal to +1, then it is not always true that A is a square. Let n greater than or equal to 3 be odd, and let the set of squares in Z mod n Z star be denoted Q sub n equals x squared mod n such that x is in Z mod n Z star. Now let J sub n denote the set of elements with Jacobi symbol equal to +1, i.e. J sub n is x an element of Z mod n Z star such that A over n equals 1. A over n equals 1. The set of pseudo-squares is the difference J sub n with Q sub n taken out of it. There are two important cases for cryptography. Either n is prime or n is the product of two primes. N is a prime p, Q sub n equals J sub n, and the order of Q sub n is n minus 1 over 2. N is the product of two primes, n equals p times q, then Q sub n is a subset of J sub n, and the order of Q sub n is the order of J sub n minus Q sub n, which is p minus 1 times q minus 1 divided by 4. The sets Q sub n and J sub n will be seen to be important in a number of algorithms and protocols, especially in the case where n is a product of two primes. Finally, we look at how to compute a square root modulo a composite number n equals pq.